Hi, my name is Hyun Park. I'm going to talk about my project on neural network and TensorFlow in finance. My project's goal is using neural network and try to predict S&P 500 return direction. Although the topic I chose was neural network and TensorFlow, I'm going to add interesting aspect of doing the same thing with different programming language R. It will provide a good opportunity to compare how both languages approach neural network and how the results are different. I will demonstrate visualization capability of both languages and also compare the results of the models I structure to solve the problem predicting S&P 500 return direction. Neural network is a computation model that is used in machine learning. Its idea studied from trying to mimic how human brain works, focusing on neurons. A single neuron is very simple. However, neural networks' advantage lies in being used as an arbitrary function that can learn from the output. And this advantage enables deep machine learning and is capable of dealing with complex models. As financial industry develops, there are a number of applications that neural network plays or can play an important role. Either financial value determination as stock market returns or stock price itself, or behavior classification such as predicting credit card fraud. Neural network has great possibilities in financial applications. TensorFlow's biggest advantage is its visualization capability. Its graph provides intuitive understanding of the flow of information in a model. Also, Google's support in developing is something that opens lots of doors for TensorFlow. However, it might be difficult for some programmers who are not familiar with machine learning to understand the concepts of every element of TensorFlow, such as initializations, session running, or placeholders, and so. In comparison, R's neural net library provides simplicity in building a neural network model. We will see how simple it is later with actual codes. However, neural net in R is trading off its simplicity with flexibility. It has fixed ways of loose computation, optimizer, and so, which is also shown later. The financial data I'm going to use for demonstration is 6 different stock market prices from different countries. Leveraging the time difference of different countries' stock market, my hypothesis is that stock market price movements from earlier time zone countries might be used to predict the stock market price movement of later time zone country. So I collected last 5 years of daily prices of S&P AXS 300 from Australia, Nikkei 225 from Japan, Hang Seng Index from Hong Kong, DAX from Germany, and FTSE 100 from London as predicting variables, and lastly S&P 500 from New York as target variable. It is important to use the return value, not the absolute values, to eliminate any influence by different currencies or currency denomination. I also incorporated the fluctuation of the price, and 80% of the data will be used to train models and last 20% will be used to test model. I have built a simple neural network model with one hidden layer and one node as shown in the left plot, and a complex model with 2 hidden layers, 5 nodes in the first layer and 3 nodes in the second layer as shown on the right plot. Before going into building models in TensorFlow, I need to show you how we converted the output data. We are using a form called one-hot coding. Each class, in this case positive return or negative return, and each class choice will be an entry in an array. If the S&P 500 return is positive, array should be 1, 0, and if it's negative, it should be 0, 1. So first, simple model in TensorFlow. First, placeholders should be set for inputs and outputs. Please note that the shapes of these placeholders should be defined correctly. The input has 11 variables, which is set with num_predictor, and the output has two classes as described before, positive and negative return, also defined num_class. As we set our variables, weight and biases, and our model will be looking like this as shown with model. Softmax cross entropy with logis will return cost value that we are going to try to minimize with optimizer. And accuracy will be the value of how many predictions were accurate. We have used Adam optimizer in our model. Two-layer model is not so different from simple model, besides more weights and biases since its shape needs to be different. Each output of layers will go through ReLU, and finally predicted output is calculated in the same way as the simple model. Then we initialize all variables, run the session. Epoch is in both model is set to 100,000. I will discuss the result of the models later. In R, it is very simple to build a neural network model. It only needs one line of code to do the job that TensorFlow needed dozens. More in detail, you need to activate library called neural net first. And in neural net, define what variables will be target variable and predictive variable. Then assign data frames that contains those variables. Neural net object has a component called net.result, which is the predictive output. Comparing to the real output value, we calculated train error as shown here. Test error is computed in a similar manner. Two-layer model building in R only needs one more argument in the function, hidden. As you can find here, we can define hidden layers should be 2 hidden layers, 5 nodes in the first one and 3 in the second one. We needed to adjust other arguments as well. As seen in the default value in neural net, step max is set as 100,000, which was too low for two-layer model to converge. I had to increase this to 1 million so that the model itself is successfully converged. Threshold argument specifies the partial derivatives of the error function as stopping criteria, and I had to increase it from 0.01 to 0.05. Training and test errors are computed in the same way. Before going into details, I would like to show you the effect of number of nodes to accuracy. I have ran 10 repetitions of calculating train and test accuracy of neural net models with different number of nodes. I use the same data set we are investigating. As seen here, train accuracy increases as the number of nodes increases as well. However, test accuracy decreases. It signals that larger number of nodes might look like it's performing better, but it has risk of overfitting. We should remember this when we are comparing the accuracy of simple and complex model later. As mentioned before, TensorFlow has strong visualization capability, especially with this graph that shows how information gets flowing. You see how each model information is flowing from the input to result. And complex model graph has 2 layers you can see from the graph, which is what we intended. Visualization of neural net in R might not have a function that can show something like graph from TensorFlow, but it also has good graphs. One thing that I like was these simple plots that shows the model structure as shown on the left two graphs. Other graphs or plots are examples that shows neural network models prediction in R. It is colored with the real output value, and we see that it does a pretty good job of classifying between red and black. Before analyzing the results, we should be careful. As mentioned before, TensorFlow has more flexibility in building a model. Depending on which optimizer or learning rate I use, the accuracy range between high 70s to high 80s. Just comparing the performance of two languages with these accuracy values would be comparing an apple to pear. Anyway, the results from the models are shown here. In almost 80% of the time, we are correctly predicting the return direction. It is very high accuracy and proves the superior performance of neural network. We can conclude that we can predict S&P 500 return direction 8 out of 10 times correctly using a different country's stock market return values. Thank you for listening.